a torch, and then I promise the video will be over before it burns out. Now, when working with VFX, I like to have a small library of assets.
Okay. Day 2. Okay, I'm gonna start a new project because this one, like, it broke. It broke bad. Yeah. Let's see.
Ready to experiment with, especially textures. So I've gone ahead and bundled together a bunch of my favorites into an asset pack that you can download for free using the link below. It contains all of the assets that I'll be using in this video, from sprite sheets with cool pixel art effects, to textures that are perfect for particles, and even some flipbooks. Everything is under the CC0 license, so it's free to use and there's no requirement to credit. Thanks to the original creators on
Okay.
We'll get a good overview of the many terms thrown around when working with 3D assets, we'll nerd out on workflows and how to best use these assets in Godot, and finally, we'll learn how to render them beautifully in the engine. This video is meant to serve as an overview, not a follow along, so lean back, grab your favorite snack, and let's figure this out. But first, this video is sponsored by Senma. If you want to know more about Godot, make sure to check out Senma Academy. They offer great beginner and intermediate courses, including a free introductory course on Godot. Senma combines fun and practical learning through professional video tutorials, written lessons, and interactive quizzes. And what's really cool is that you'll build real projects across various genres, from RPGs to bullet hells. Senma also has a wide range of courses on Python, Unity, Unreal, and other essential tools. With a single subscription, which includes a 7-day free trial, you unlock over 300 courses. Use the coupon code below to get an extra 20% off the first year of your Senma subscription, on top of any existing site-wide discounts. The offer is valid for the first. Create a 3D scene, name it main, and save it. We can create something to look at by going plus or hit Ctrl A to add a new node. We'll search for mesh instance and add the mesh instance 3D. And here Godot supplies us with some primitive meshes that we can use. I'm going to choose a new box mesh, and we can of course orbit this box by holding down middle mouse and using shift middle mouse, and zoom using scroll. Just like in 2D, selecting something and hitting F will focus the view on that node, and by holding down the right mouse button and use. And this is one of the things that Godot makes very easy with its built-in CSG nodes. CSG stands for constructive cell geometry and allows you to quickly make levels and props by combining simple shapes. And in the end, you can even export your greybox scene and bring it into a 3D modeling program such as Blender to use as a base. So let's try it out. When prototyping, I almost always work with snapping enabled. So at the top here, we can enable snapping or press Y, and we can configure the snap under transform, configure snap. I'll set this to 0.1, 10 degrees, and 10% scale. Now we can add a new node and search for CSG, and as you can see, there are different ones in here. I'm going to start with a box. And drag on the handlebars to scale it. If I hold down Alt, it's going to mirror on both sides. And a nice thing about this is that we don't need to add collision separately. We simply go to the right here and enable use collision, and now we can collide with it. So let me just make a quick wall here. And let's say we wanted to add a window to this wall. In this case, we can use subtractive editing. So under this CSG box, I'll add a new CSG, and this time let's make it a cylinder. I'll position this where I want the window. And I'll make sure that it sticks out on both sides of the wall. And then to subtract this from our box, we simply change the operation from union to subtraction. And as you can see, we have a round window. And we can very easily adjust this to do all kinds of things. Say we wanted this to be kind of an archway instead, I would simply drag this down and scale it. And we have an archway. We can also increase the sides on the cylinder to make it look a bit nicer. Very cool. And you can do a lot more with CSG and Godot, but this is enough to get started. So let me put together a quick prototype using these techniques. Oftentimes when making levels, I will go to the top right here and click on the axes to change to that view. Just a really nice way to view everything from the side or the top. And to exit, I just click and drag with middle mouse. Now sometimes I will use a CSG combiner node, so let's hit plus CSG combiner, and this will combine all child CSGs into one. So for static geometry like these rooms, for example, I can take pretty much everything and put it under this one CSG combiner. Just remember to check use collision on that node since everything is now one. And so I've blocked out these two rooms, and I've intentionally left them pretty blank. At this point, I'm starting to get ideas for how this scene might look in my head, but for the gray box, I've concentrated on just getting a rough layout. I also know that I'm going to be using tileable assets for the walls, so I've stuck to simple 90-degree angles. Feel free to get as crazy with this part as you like, or exclude it completely. Not all projects need a gray box. Keys, and even jump using space. To get control of our mouse back, we hit escape. And if we in games, I call it the Proto controller. You can download it for free. It's under the CC0 license, so you can use it for anything. It's designed to be simple and has basic movement with options for jumping, sprinting, and a free fly mode that I find super useful when testing. To import, simply take the Proto controller folder and drag it into your add-ons folder in Godot. If you don't have an add-ons folder, you can simply go ahead and create a new folder, name it add-ons, and now we can drag our Proto controller in there. And that's it. We can now go here, take the Proto controller scene, and drag it into a gray box level. We can get rid of the camera we created before, and now when we play, we can look around, move using the arrow keys, and even jump using space. To get control of our mouse back, we hit escape. And if we go into the controller, we can see that it's super simple. Again, this is intended for easy prototyping, so I've kept it very bare bones. It has a character controller to drive movement, a mesh instance for temporary graphics, a collision shade, and under the head node is a camera 3D. The script references the collider and head node, so leave them be unless you want to modify the script, which if you want to is as simple as clicking the script button, and here is all the code. On the top node, we can choose which features we want to include, as well as adjust some speeds. I'll enable sprint and free fly. We just need to make sure that we also go under input actions and find the appropriate keys. And this is exactly the same as 2D, so to add input, we go project settings, input map, and here we can add actions for all the things we want to do. I'll add some for the movement as well so that I can bind them to my own keys. And now that I have the actions, I can bind keys to them. And to put this into our controller, we just take these names and put them into our input actions. And now if I play, I can move using the right keys, I can even sprint, and I can toggle into free fly mode, and of course toggle right back. Awesome! Now we can make levels and start testing them, so we're almost done with functionality. But I quickly want to touch on physics. 3D physics works much the same as if you're using Godot 4.4 or later, Build is already part of the engine and just needs to be enabled by going project settings, scrolling down to physics 3D, and setting the physics engine to Jolt physics. It'll ask us to restart, and Jolt is now enabled. On previous versions, I'm building this in Godot 4.3, we first have to install it as an add-on. So we'll go to the asset library, we'll go online, search for Godot Jolt, we'll click and download, hit install, save and restart. And now we can enable it in the same place under project settings, 3D physics. We have to check advanced though, and under physics engine, we have Jolt physics. And again, we'll have to restart. And as you can see, we didn't have to change anything about our game. We can run it and move around just as before, but now all the physics nodes will use Jolt instead. So that's how we can start prototyping and building functionality for our 3D game. Because there's more to 3D than just making an environment. Now this is where I see a lot of people get confused, and that's an entire video in its own right. Because internally, even at 0, the material reflects a tiny bit, just like in real life. A metallic map requires only one channel. Note that once in a while you might run into something called a specular map. This is an alternative to the metallic workflow that Godot uses and is not supported. Roughness. How smooth or rough is the surface? A material with a low roughness value results in sharp reflections. As the roughness increases, the light becomes more scattered and the reflections start to get fuzzy. A roughness map also only requires one channel. Some assets provide a smoothness map instead. This is the same as roughness but inverted. In this case, I would recommend inverting it in an image editor before importing to Godot. Normal. Here you can add a normal map to simulate depth. It changes the way light interacts with the surface to display smaller shape details. However, the mesh is not actually affected by a normal map. Because of this, the effectiveness will vary depending on the viewing angle. A normal map uses the RGB channels. Be aware that Godot uses normal maps in OpenGL style. Some normal maps that are created for DirectX will appear inverted. If your normal map doesn't look right, you can go to the import window and select normal map invert Y. This will convert it from one style to the other. Ambient occlusion. Here you can add an AO map that affects how much ambient light reaches the surface. In other words, it can darken the parts of your model where light has a hard time reaching. And it uses one channel. Emission. Does the surface emit light? We can set this manually or use an emission map. But this is more pertaining to lighting, so we'll move on. There are of course many other types of maps like height or refraction, but these are for more advanced use cases, so we won't go into them here. At this point you might be thinking, that's a lot of textures for just one model. And many games will definitely only need a fraction of them. But if your game needs them all, it can be a challenge to fit that many textures into the game. Because of this, it is common to use an ORM texture and material. Remember that ambient occlusion, roughness, and metallic textures only require one channel each. This means that in practice they can be combined into an ORM texture, where each map occupies either the red, green, or blue channel. Godot fully supports this workflow with a version of the standard material called ORM Material 3D, which can be combined with regular standard materials without issue. And on the subject of materials, for some workflows, the 3D artist will set up all the material properties in the 3D software. In this case, the textures will often be packaged with the model file. This is called packed or embedded textures. Here, for example, I have a barrel, which just consists of a DLTF. The material and texture has already been set up in Blender and packed into the file. So if I import it, Godot will extract the textures and place them next to the DLTF. And the model is ready to use. We can always go under the import settings, and at the bottom, under embedded image handling, choose what happens to the textures. As you can see, this is set to extract by default, and so it appears next to the model. And if we want to, we can also extract materials. So if we double-click the barrel, go under actions, there's an option here to extract materials. So I'm just going to extract them in the same place, and now we can configure the material. This is useful because not all materials in your 3D program will transfer perfectly into Godot materials, in which case you might want to adjust them here. Alright, so our test is imported and looking great, but how do we actually start using it in our game. Now if we play the game, I can run right through it, so we'd at least want to add some kind of collision. And what I see a lot of people do is go here to open scene and choose new inherited. This creates an inherited scene based on the GLTF file. What this means is that we can add new nodes to the scene and even override some properties, but we can't modify the original hierarchy, which turns yellow to indicate this. So we could add a node here, we can add a script, make some changes, and when we're satisfied, save it as a new scene that we can use in our game. And this works, but there are a few problems. First of all, using inherited scenes quickly gets very confusing. What's part of the original asset and what's not? Also, it breaks very easily. If I make a change to the asset and it gets re-imported, it can be hard to predict what happens to the inherited scene, and your changes might get removed. And doing it this way means that we are basing our game functionality on a graphics asset. This is generally a no-go, especially in more complicated scenarios. In fact, most of the time we're doing the exact opposite. We build functionality without fancy visuals, and then bring in those visuals as we'd like. So instead of using this to create an inherited scene, I recommend that you use nesting. With the nested approach, we create a new scene that we have full control over. So I'll make it a 3D scene, name it chest, and here we drag in our model. This allows us to free create and configure gameplay nodes and then import or swap out our graphics as we see fit. Then when we are happy with it, we can save it and start using it in our game. This approach is also much more stable because any changes to the GLTF file won't affect our game logic. It will just update this one nested scene. Of course, it might happen that you need to reference something inside the nested scene. I would generally advise you to be careful when doing this because, again, things become more likely to break. But if we need to, we can expose the child nodes of the scene by enabling editable children. If you find yourself doing this a lot, perhaps it would make more sense to split the asset into multiple GLTF files instead. Take this chest here, if I needed to access the lid to open it, I could export the lid as a separate file. Just an option. Now, there's actually a third way of structuring your scenes that I personally like for a lot of reasons. Unfortunately, it currently has a very big drawback. For this technique, we also use a separate scene, and again we drag in the model. And then we press make local. What this does is that it breaks the connection to the GLTF scene. This now gives us full control over the original asset, which means that we can pick and choose what we want and reorder the hierarchy. So it has some clear advantages. It's very flexible and makes it easy to separate function from visuals. But I mentioned there was a drawback. As of making this video, this is Godot 4.3, when we press make local, Godot will take all the mesh data in the GLTF and store it in the scene we created. That means that if we save the scene before pressing make local, and look at the size, it's very, very small. But if I now go in and press make local and save again, we can see that immediately the scene grows by a lot. Now this might be fine for very low poly models, but if the mesh is more complex, it will bloat your scenes a lot, which is not a good thing. Remember that at some point this scene needs to be loaded by your players, and if it's big and bulky, that is going to take longer. Now improving these workflows is something that is being actively discussed in the Godot community, and I'll provide some links to where you can read more if you're interested. But for now, these are the 3 ways.
Okay.
And save again, we can see that immediately the scene.
FPS tutorial series version 2. So we're the path state and then head to its sigil. I'm going to state machine script so it's all in one. Will extend from the center of our camera and the
Ah. 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 Okay. Be a big shot. Be a big shot.
Back to the bean shape and the mesh drop down. We're going to create a collision shape from the mesh by going to this menu and selecting create to move around and even jump out of the mode. The next step is adding our own input map. We can the rotation of the head depending on how much the mouse moved relatively, multiplied by the sensitivity, which we're going to add as a constant. Here we're keeping the rotation axes separate, so we're only rotating the head on the y-axis and the camera on the x-axis to avoid the whole rotation order mess. You'll also note Notice we're rotating the head y angle depending on relative x distance. This is not a mistake, but rather just a byproduct of how translating mouse movement to camera rotation works. When we move the mouse left and right, we want to rotate around the y-axis, which is pointing up, and when we move the mouse up and down, we want to rotate around the x-axis, which is pointing to the side. So after putting all this together, we can finally look around.
I think I need to add an environment. Yeah, I can just.
Our sensitivity might be a little too high, and also we can do cartwheels with our head. So let's use the clamp function, which can limit the rotation of our camera to a minimum.
Why did it just mute?
Also getting tired of staring at a whiteboard with nothing. Minimum and a maximum.
There we go. Mm. I just crushed my fingers. I just crushed my fingers. Yeah, okay. You mean it's not frickin' Farty Bob? Dog. Okay. Oh my god. There we go. What? Okay. Yeah, that feels good. It's like buttery smooth. Okay.
In this video, we'll add footsteps in sync with the head bobbing. This is a follow-up to my head bobbing tutorial. If you haven't watched that yet, go do that and then come back. And if you find this helpful, please subscribe. So let's slide in. So start opening up Godot. I'm going to start by adding a new node. This will be Audio Stream Player 3D. Hit create, and we want this at the bottom of the player, so it's perfectly positioned right now. I'm going to rename the audio stream player to Footstep Audio, and I'm gonna keep 3D. Footstep Audio 3D, pretty good name. Right click on it and access as unique name. Go back into the script and we're gonna add two new variables. One is for when the footstep sound can play, and we're gonna make this true. And another one for when we land on the ground. If we go down into the physics process function under move and slide, we can check if we go down into the physics process function under move and slide, we can check if the footstep landed is false, so if it's not true, and if we're on the floor, that means we landed on the ground. So I'm gonna add a comment and landed. Then we want to drag in the footstep audio 3D and and then we can do dot play, and it will play the audio. Then we can make a elif after this, checking if the footstep landed is true, and if the is on floor is not true. That means we have just jumped, and if we jump we can play the audio stream player. So that's the footstep. Audio 3D, and then we can do play. And after we make these checks, we make the footstep landed equal to is on floor. And if we hover over is on floor, we can see that it returns true based on the move and slide function. So that means that when we call the move and slide, is on floor is also updated, and then at the end of this we update the footstep landed, and that's equal to is on floor, and that allows us to easily check if we have jumped or landed. Then after that we can go into the headbob function, and above return then we add a new variable that we call footstep threshold, and that is equal to negative headbob amplitude, and then we do plus a really small value. We'll tell you why later. Then we check if the headbob position y is more than the threshold, so then we want to do footstep can play equal true, and then we can make a elif statement if the headbob position y is less than the threshold, and if footstep can play is true.
Okay.
So, mirrors. What are they and how exactly do they work? I mean, in a video game, because I definitely don't want to get involved in the physics and mathematics behind mirrors in this video. Now, you've probably seen a lot of mirrors in video games. Some can look better than the other. But how do they exactly work in a video game? We basically need to somehow create the illusion of a mirror in a way that looks believable. Now, there are a few ways that games use to achieve this. First way we're going to look into is what I like to call copying. Basically, copy whatever's in your level to make the other side, but reversed. Now, don't judge me by my level designing skills. This is just something that I put together for this video. But basically, we have a mirror now. Wow, that was easy. Now you could try adding a shader to make it look more believable, I guess. But yeah, we basically have a mirror. And you know how much I hate games when they don't show the player in the mirror. So I copied myself too and changed a few lines of code. Now you could probably develop a logic that would automatically mirror stuff like enemies and some items. Now I don't claim to know the best way of doing things or to write code that's flawless. So use this information as a hint and not as a must. Now to test the performance of this mirror, let's first test how the game runs without anything. So you can see I'm getting around 650 to 750 FPS on my PC. So now let's go ahead and try it with the mirror. and as you can see, we're getting around 450-ish FPS, and with the shader removed, we're getting around 500 FPS. Now, as much fun as this was, what about the other methods? You know, the process of duplicating every single thing in your level may not be possible in some cases, like a moving vehicle. So what do you do then? Well, think of it this way. A mirror is basically reflecting whatever light particle is hitting it. So we could use a camera to achieve a perfect mirror. So it basically works like this. The camera renders a level in its own view, and then we can use those images on a plane to get the illusion of a mirror. So for example, I made this Sprite 3D node, and I'm going to attach the viewport texture to its texture slot. And after setting it, we can see that we have the view of the new camera in our level. And so when I saw this first, I was like, we can definitely make a mirror with this, right? Well, kind of. You see, I did try to make a mirror with this, but as you can see, it didn't turn out very well. But my second version was actually looking better. But here's the thing. I used something really crazy on this one. I moved the Sprite 3D with the player, which kind of works, but it's the wrong way of making a mirror. So after coming across this tutorial on YouTube, I learned that I could use the screen UV from a shader to draw the images on a plane. He also talks about where to put the second camera and stuff, so I recommend you checking it out if you want to learn more. But here's the thing, I didn't watch the video till the end because since I'm going to learn about mirrors myself, I wanted to write the code myself from scratch. But basically, the mirror's camera needs to be positioned according to the player's camera. So here you can see I'm copying the position of the player's camera, except for the x-axis, which I'm inverting, and then I'm setting the y-axis rotation of the mirror's camera based on the player's camera, and then just copy-paste the x-axis. And so you can see it works fine here, but there's a small problem, and that is whenever I try to look at the corners of the mirror, everything just kind of breaks apart. I made some improvements in the code, and now it actually works better, but it still has some issues, and very limited. Like for example, it is so limited that when you need to rotate it, you have to change the code, so it mirrors the other axis. I wrote some code with sine and cosine to automate this process, but it had so many bugs, I just went with this. You can tell me in the comment section if you know anything about mirrors. Now to test this mirror, I'm first going to test it with a viewport resolution of 1024 by 512 pixels, which gives us around 450 FPS, which is almost the same as the copying method. I'm guessing it's because it's a small scene, and also you can see if I don't duplicate the light sources, I actually get closer to 530 FPS. So I guess it depends what you're copying. Now back to our camera method. Doubling the resolution, however, dropped our FPS to 320 FPS. Now, I don't think this method was really meant to be used as a mirror, but I mean, it kind of acts like a mirror, just a very bad one. The one that you can't see yourself in. And of course, I'm talking about the screen space reflection. Now, to use it, you need to first make a material that's reflective, and then you need to turn it on the world environment. Now, this method was meant for the reflections of the things that are already on your screen. So what's behind you is not really the part of this. Now, you can use something called a reflection probe, which you can use it without the SSR as well. It's basically a cube map. You can use this with something like reflections on a scope, but I really can't recommend it for a mirror in its real-time mode, because it can be very expensive, so just put the update on once. So I played around with the reflection settings, and I increased the reflection size, and turned on some options on the reflection probe, and you can see it actually doesn't look terrible. Let's say it's a mirror on a corner of a level. You know, it could work. Just make sure to disable the layers that the dynamic objects are on so that they don't appear stuck. And after testing it, we can see that it gives us around 530 FPS, which is almost like the copying method. Now this next method can be quite demanding on the GPU, since we're using global illumination to get the colors of the mirror. And I think it only works with static meshes, but you should be able to use dynamic lights. Now even after increasing the cell size, it still didn't look great, which makes sense because it wasn't really meant to be used as a mirror in Godot, but it can give you nice reflections and lighting, which is a win for me. And so these are the settings that I'll use to test the FPS of this method. You can see we are getting around 290 FPS, which is not terrible for global illumination, I guess. Now the other way to use the global illumination is to use voxel GI, which is generally more intensive than SDGFI, but it also works with dynamic objects. First thing you need to do is to bake your meshes. Now I got this weird banding issue on my mirror the first time I tried this, but I fixed it by adjusting some settings in the mirror's material. I also increased the subdiv size for the voxel GI to get more details. Now the scene would go darker for some reason when I increased the subdiv. After testing the FPS, we can see that we're getting around 80 FPS, which is by far the worst performance. Now honestly, you wouldn't really use this as a mirror anyways, so it was all fun, I guess. Now I came across this ray tracing add-on, which looks like it might be able to do some mirrors, but unfortunately I think it's still a demo and you can't use it on meshes on your main scene. But it definitely looks cool and looks like it might be improved in the future. Okay, so that's the end of this video, I guess. I couldn't really find any other methods to fit in this video.
Imagine being inside you.